We are jumping right into Unit 1, and we are talking about water. Now, I think everything on your notes should be underlined on the slides. If not, we'll figure that out together. My goal for you is to be able to list the qualities of water. Hi. Um, every single day. My goal for you is to be able to list the qualities of water and describe why those properties are important in maintaining life. So we are jumping straight into biochemistry. We'll talk about water today. You actually have a pre-lab for the last couple minutes of class because we're going to do a lab first thing on Monday. So we're not going to, it's about water. So just kind of prep for that. And then next week, we get to start talking about biological macromolecules. So carbs, lipids, proteins, nucleic acids, which is super exciting. But first, we've got to talk about water. Water is polar. If you do not know anything about water, at the end of the day today, know that water is polar. It is because of this polarity that it is so important to life. If water was not polar, life would not exist. This quality is the reason a lot of what we do happens. So, being polar means that it has a positive end and a negative end, much like magnets have a positive end and a negative end, or the Earth has our poles. The reason water is polar is because it is shaped kind of like a giant Mickey Mouse head. It is 2 hydrogens and an oxygen. Electrons like to spend time near the oxygen. So these molecules are covalently bonded together, which means they are sharing electrons. And those electrons like to hang out near the oxygen. So every water molecule is negative around the oxygen molecule and positive around the hydrogens. So on the little water molecules you have on either side of your title, I want you to draw little pluses and minuses. Our hydrogens are more positive. Our oxygens are more negative. Our charge is distributed unevenly. Questions so far? Doing all right? This is the first time I'm doing notes guides in AP Bio. I typically go faster whenever we do these. So if I move too quick, or if you want me to go back, just raise your hand. I will never, ever, 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 ever be offended if you say, hey, Ms. Carter, can you slow down? Can you go back? I know I talk really fast sometimes, especially when I get excited. And who wouldn't get excited about water? Right? So, water forms 2 types of bonds. Polar covalent bonds, which happen between the hydrogens and the oxygens of a singular water molecule, and hydrogen bonds. So this right here is our covalent bond. And this right here is a hydrogen bond. Now, hydrogen bonds are very, very special. Does anybody remember from their chemistry experience what a hydrogen bond is? That's going to happen a lot. covalent. Right. It is a intermolecular force, right? It's not sharing or transmitting electrons. A hydrogen bond isn't really a bond. It's more of an attraction. Just like magnets stick together when you get the positive and the negative ends near one another, water molecules stick together whenever you have the positive and the negative ends near one another. So every glass of water, every raindrop, every dewdrop has all of these hydrogen bonds that are holding those water molecules together. That's why water feeds up. It likes to stick together. Hydrogen bonds, like I said, are attractions between our positive and negative ends of our molecules. Polarity allows for hydrogen bonds, and we get cohesion and adhesion out of it. So your little cohesion side is this. Your adhesion is this. And I really, really, really love the little diagram that I've got between them, or between cohesion and adhesion on your notes sheet. Cohesion is the force of water molecules sticking together. They're hydrogen bonds between water molecules. Co, like buddies together, adhesion. Adhesion is water sticking to other substances. So when you read a measurement on a graduated cylinder, there's something special you have to do. Right? Every time that you pour water or a substance that is mostly water into a graduated cylinder, you get something called the meniscus, right? Where the water sticks to the edges of your graduated cylinder. Like this. And you always read from the bottom of it. That's because adhesion has the water molecules sticking to the sides of the graduated cylinders. That's adhesion. Cohesion is what we're going to be working with mainly with our lab on Monday. Surface tension is how difficult it is to break or stretch the surface of a liquid, and water has really, really high surface tension. That's why sometimes when you pour too much water in a cup, you see the bubble over the top. Because those water molecules are sticking together so tightly that they don't want to let go. That's why those little pond skater bugs can kind of walk on water, is because they're not heavy enough to break the surface tension and fall through. All because of hydrogen bonds. That's why whenever you stick a straw in your drink and cover the top of it, you can lift the straw out and then release vacuums, and the surface tension of the water at the bottom of the straw isn't going to break. Questions? All right. Hydrogen bonds give water a lot of special properties, and one of those properties is a very, very high specific heat. When we talk about heat in biology, we're talking about transferring thermal energy. So heat is just atoms moving very, 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 very quickly, right? So when atoms are moving very, 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 very quickly, and they move from one thing to another, if you put a pot of water on the stove to boil some spaghetti, right? Those very, 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 very fast-moving atoms in the stovetop will heat up the metal of your pan, which will transfer to the water. Heat is measured in calories. A calorie, this should be a big C calorie, or little c calorie is the amount of heat needed to raise 1 gram of water 1 degree Celsius. Why? Because all units are made up, and we like to use water as a baseline. So they just took the amount of heat used to raise 1 gram of water 1 degree Celsius, and they're like, yep, that's our unit for heat now. Now, calorie, little c calorie, is not the same type of calorie you are used to seeing on food labels. Calories on food labels, or big C calories, or wait, this should be big C calories, yeah, is actually a kilocalorie. The calories on food labels are 1,000 of these calories that are our base unit. Why? Because scientists like to name things a bunch of different times because it can. So this is how we measure heat. Water has a special relationship with heat, what we call specific heat. Specific heat is the amount of water or amount of heat needed to raise 1 gram of a liquid 1 degree Celsius. So we measure all heat transfer in water's specific heat. And this allows us to measure how well a liquid resists temperature change. So if a substance has a much higher specific heat than water, it means it resists temperature change a lot better than water does. If something has a very, very low specific heat, it means it is very, very sensitive to temperature change. Think like isopropyl alcohol. When you rub isopropyl alcohol on your skin, if you get a cut, right, it evaporates super, super quick. It has a very low specific heat. Heat transfers into it like it's nothing. But when you're waiting on a pot of water to boil because you're very, very hungry and you want some mac and cheese, it seemingly takes forever. Because water withstands temperature change very, very well. It's why we use water in industrial power plants and steel manufacturing to cool things down, because it absorbs water very, very well. Yes, sorry. So, why does water have a very high specific heat? Hydrogen bonds. When in doubt, if there's a special quality of water, it will lead back to hydrogen bonds. Because hydrogen bonds need energy to break. You need to put energy into them to get them to break. That's why getting water up to its boiling point, getting water up to where it's evaporating and breaking those hydrogen bonds takes a lot of energy. The more hydrogen bonds, the more heat can be absorbed before they start to break. This is why we use water to cool things. Let me know if I'm going too quick. Questions so far about hydrogen bonds, specific heat? Anything like that? All right. So, water's special relationship with heat also gives us this really cool feature called evaporative cooling. And you can thank this property for why we sweat. When water evaporates, the hottest molecules leave first. So evaporation has our hottest, most rapidly moving water molecules leave whatever we're doing. And when those hot molecules leave, the surface they are leaving is cooler now. This is why whenever classrooms get up to 76, 80 degrees and we start sweating, that sweat evaporates and it cools us down. It's kind of really cool. That's heat with water. We're going to talk about the absence of heat with water as well. One very, 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 very important quality of water is that ice is less dense than liquid water. It is very rare for the solid version of a molecule to be less dense than the liquid version. Because usually when we think about solids, liquids, and gases, solids have molecules super packed together. Liquids are kind of moving around a little bit. They've got some more space. And gases are here, there, and everywhere. But these hydrogen bonds, when water freezes, actually keep the molecules distant from one another. And they form what is called a crystal lattice. Think like the lattices people have plants growing up on the side of their houses. They keep the water molecules organized. And there is air trapped between these water molecules. That's why ice floats on water. If ice did not float on water, all of the ice in the oceans would sink down to the bottom of the oceans, and then the entire oceans would freeze over. Would not be a good time. So, the fact that ice is less dense than water is a super important concept. But water does more than just temperature fluctuations. Water is an excellent solvent. It's a little basic vocab. A solution is a homogeneous mixture. Homogeneous just means like evenly distributed. There's not chunks or anything floating around in it. Think like salt water, sugar water, good coffee. There's not stuff floating around at the bottom. A solution is a completely homogeneous mixture. There are two aspects to a solution, a solute and a solvent. The solute is dissolved and the solvent does the dissolving. Water is a very, very, very good solvent. When you want to dissolve something, water is typically your way to go. And any solution where the solvent is water is considered an aqueous solution. So if you are given a phrase or a problem or a question that says a 30 molar salt aqueous solution, that means there is salt dissolved in water. These aqueous solutions are super cool because of hydrogen bonds. Hydrogen bonds form hydration shields, which sounds a lot cooler than most of the stuff we're talking about. Hydration shields. Essentially, when you've got a ion, something charged, that you're dissolving in water, those charges attract the different ends of our water molecules. So when you put salt, which is a sodium and a chlorine ion, in water, chlorine is negative, which means all of the positive hydrogen ends of our water molecules are going to kind of storm that negative ion and surround it. Kind of like those little games where you've got like a magnet on a stick and you move the little iron shavings to give the guy hair. I don't know what they're called. You know what I'm talking about? Like old school toys. Oh, that'll make sense later. I'll figure it out. Same thing with the sodium. Sodium's a positive ion. Whenever the positive ion gets dissolved in water, all the negative ions or negative ends of our water surrounds it, and it forms a little shield. That's why they're so easily dissolved. All the water wants to get near it. when we're talking about what gets dissolved in water and what doesn't, we've got a bunch of different interactions. So ions and other small non-ionic polar molecules will dissolve. So if it is an ion or if it is small and polar, water will dissolve it. So like sugar isn't an ion, but it's small and it's polar, so it'll dissolve in our coffee in the morning. If you remember from Bio 1, we've got some fun words, hydrophilic and hydrophobic. Hydrophilic are water-loving interactions. Hydrophobic are water-hating interactions. So when water sticks to things, when water is attracted to things but can't quite dissolve it, that is known as a hydrophilic interaction. When water is repelled from things, this is a hydrophobic interaction. Think oil and water. They don't want a hydrophobic interaction. All right, this leads us to acids and bases. Acids and bases. We can thank water for our ability to measure pH. When in any solution of water, water can dissociate into hydronium and hydroxide. Hydronium and hydroxide. Hydronium is written as H+, little underlining thing, underlined the plus sign too, apparently. H+, but H+ does not exist in solutions. Rarely, if ever, is just a hydrogen ion floating around. It is always, always, always H3O+. Here, I'll write these out because it's a little funky. I've lost my pen again. It's in my back pocket. This is H+. That's how we usually write it out because it's a lot more simple than always writing H3O+. That's hydronium, and then hydroxide is OH-. So this happens freely in any aqueous solution. And our hydronium and hydroxide concentrations is what helps us measure acids and bases. An acid is anything with a very, very high hydronium ion concentration. So you'll see concentration be written out as brackets. So hydronium concentration can be shorthanded to that. This shorthand saved me writing paper notes in college, because writing out the word concentrate forever. So hydronium ion concentration, when that is high, that means we've got an acid. Things like vinegar is acetic acid. The powder on the outside of Sour Patch Kids is sugar mixed with citric acid. Our tongues detect acidity as sour. That's why whenever you have sour candies, you are just intaking usually citric acid. That's why if you sit and you eat an entire bag of Sour Patch Kids and your tongue starts to feel weird, it's because you've burned yourself with acid. It's an acid burn. A very, very mild one, but maybe don't lick the powder out of the bottom of the Sour Patch Kid. Bases are characterized by a low hydronium ion concentration or a high hydroxide concentration. So if we've got a lot of OH minus, We've got a high hydroxide concentration that gives us a base. Things like bleach and laundry detergent and soaps. Those are bases. Not as much fun as acids. Questions here? All right, this gives us our pH scale. We won't go into like the calculations of pH. It's a little bit more chemistry than AP Bio people want you to do. Essentially, pH is the negative log of the hydroxide concentration. That's not something you'll need though. We've got bigger things to mess with. But knowing that water dissociates into hydronium and hydroxide, and that is what leads to acids and bases, is where we're at. That's what we need. And then we can finish this up with buffers. A buffer is a solution, an aqueous solution, consisting of a weak acid and its conjugate base. Or vice versa. Weak base, conjugate acid. Buffers are important because they essentially resist pH change the way water resists temperature change. They help our pHs remain steady, which is super important for things like homeostasis, which we'll talk about when we talk about cell biology. That was a lot faster than I thought it would be. I'm still working out time and stuff. So here is what I've got for you for today. We still have like 20 minutes. We'll figure it out. Like I said, on Monday, we have a surface tension lab, and I have some pre-lab questions for you. There are only 5 of them. So I think we'll be able to get them done in class. So if you could do the pre-lab questions and take a skim of the procedure. Going over the procedure before a lab will save you immensely. Take it from someone who has gone into an organic chemistry lab with no clue what was going on and got very lost very quickly. You'll figure it out, but it'll make life a heck of a lot easier if you skim through that procedure first. So on Monday, we will go over these pre-lab questions, make sure everybody's got what they need to get started, and you will partner up to knock out this lab. Questions here. Yes. Give me 1 second. Mm-hmm. Mm-hmm. All right. Anything before I let you loose? Alrighty.